everyone, welcome to week 2. For today's lecture you will need your periodic tables. You'll need to print off homework number 3. You'll notice that most of the problems for this week are in the textbook, so you'll also need to have your textbook handy. You'll need your pink sheet and your calculator. Okay. Before we get started, there are going to be some new timing issues as to when your homework and quizzes will be due. So please look at the home page of your Joule listing for this course to find out when your new dates and times for having your assessments uploaded are. They won't be anything earlier than what you're used to. I have different ideas on revamping the due dates, so it should be easier for all of you. Okay, so if you take a look at your learning objectives for today, you'll notice that we're going to be going through all of the mole. And I just want to take that first section of your learning objectives, and I'm going to flip-flop these two things in today's lecture. I'm going to start teaching molar mass. So just logistics. Okay. So molar mass is a concept that we'll be using throughout the rest of our time together. So it's a very important and pervasive concept. So we'll do quite a few examples of how to calculate molar mass. So molar mass is the mass per mole. Don't worry about this for right now. Of a compound or element. And the way it's calculated is by looking at the mass number on your periodic tables and adding those things up for each individual element in the compound. So the main thing that we're going to be doing is looking at the mass numbers on our periodic table. So if you take a look at your table, you'll see in blue, I'm just looking at nickel here, number 28, nickel. The little numbers in red, and for nickel it's 58.9332. This is your mass number. And it's in red on your table. Now, what I want us to do is, because there are so many decimal places for each one of these mass numbers, is to always use 2 decimal places. I'm writing this in red. I hope that you highlight this in your notes, or if you're just printing off of my notes, make sure you highlight or circle this part. Always use 2 decimal places. If you don't, I will mark it wrong for not using the correct number of significant figures. So make sure that you do this. Okay, all you're doing here is looking at the periodic table and adding stuff together. It's not very complicated, but because it's pervasive, like I mentioned, let's do some examples. Let's start out with something easy. Sodium chloride. Every element that you see in your compound has a corresponding mass number on the periodic table. We need to add all those together in order to calculate molecular weight. So if you wanted to write this down in your notes, molecular weight equals mass number of all elements added together. So for sodium chloride, we are going to find sodium on the periodic table. Sodium is element number 11. It has a formula weight of 22.989. So you're going to have to do a little bit of rounding. 22.99. And chlorine is element number 17. it's 35.45. Now to calculate the molecular weight, or the molar mass, all we have to do is add these two things together. 22.99 plus 35.45 equals 58.44. Now remember when we said at the beginning of our discussion, molar mass is the same thing as molecular weight, and I use these terms interchangeably. It's the mass per mole. This is your unit. So here, our unit, we always have to have numbers with units, otherwise numbers don't mean anything. Our unit is always going to be grams per mole, mass per mole, grams per mole. This is how we abbreviate the word mole in chemistry. So mark this down for future reference. Okay, that was an easy one. Let's do something a little bit more tricky. Oxygen occurs in nature as what we call a diatomic element. So diatomic, di meaning two, atomic meaning atoms, so it occurs as two atoms. Now, in order to calculate the molar mass or the molecular weight of this compound, you need to take into account however many times each element occurs. So here you have oxygen, 15.99, but there are two of them. So we're going to multiply this mass number from the periodic table by 2. And then we get 31.98 grams per mole. Remember that grams per mole is your unit, and yes, you have to have that unit on anytime you're collecting or calculating molecular weight, otherwise it is wrong. Okay, so let's do another example. We're going to get progressively trickier. How about calcium hydroxide? Here we have calcium. You can find that on your table. That's easy. Let's break each of these things down. We have calcium, 40.08. And then we have oxygen and hydrogen. But there are two oxygens and two hydrogens. That's what this bracket means. So whatever our oxygen and hydrogen mass numbers are from the periodic table, we have to multiply those by 2. So 2 times 15.99 and 2 times 1.008. Now, I know that here I'm using 3 decimal places. It's okay to do that for hydrogen, for nothing else. Okay, so if you add all of this stuff up, now if you do happen to have a fancy calculator that I have, you can program elements into your calculator so that you don't have to so that you don't have to type them in every time. 74.076. And what is your unit? Grams per mole. Now, you've got this extra 6 here, so really you should have a bar over the 7 here. This is my habit. I will try to not do that and only use 2 decimal places just for you. Okay, let's do a bunch more examples. Okay, for this problem we have 3 elements, carbon, hydrogen, and bromine. And now your carbon and your hydrogen are both appearing multiple times. So when you calculate your molecular weight here, you're going to have to take 6 times your carbon, so 6 times 12.01, 5 times your hydrogen, 1.01, and your bromine is 79.90. That only occurs once. And that gives you a total of 157.00. Remember that you should always have these 2 decimal places in your answer. Excuse me. Okay, so let's just talk a little bit about this formula here. This number only applies to the number before it, or the letter I should say before it. But if you have something in brackets or in parentheses, that number on the outside of the bracket applies to everything on the inside. Let's take an example of that. Here we have lead 2 nitrate. Here you have nitrate as your polyatomic ion. You have NO3, but the whole NO3 species occurs twice. So this formula is really like saying PbNO3NO3. For obvious reasons, we don't write chemical formulas this way because it gets very tedious. So, looking up here, this 2 only applies to everything that's within the brackets. So it applies to that oxygen and to the nitrogen. It does not apply to the lead. So there's only one lead. Lead is one I gotta check for. There's only one decimal place on the periodic table for lead. Don't worry about it. Okay, now there are 2 N's. N is 14.01. And now there are 2 of these nitrate groups. Each nitrate group has 3 oxygens. So how many total oxygens do you have? No, you don't have 5, you have 6. Remember it was like writing NO3, NO3? Well, if you were to add these things up, you would have 6 total. So whenever you have the brackets, you're going to take your outside number and multiply it by whatever is on the inside. This is important. So we have 6 oxygen, 15.99 times 6. Now your total answer then is going to be 331.16 grams per mole. Don't worry about the fact that this number only has 2 decimal places, or excuse me, only has 1. That's okay. And the fact that this has 2 is also okay. Okay, let's do some more examples. This is a great one. Ammonium phosphate. Okay, see if you can think about this one on your own. I think you should pause it and see if you can come up with the correct answer. Okay, so remember that this 3 applies to both the nitrogen and the hydrogen. So you're going to have to multiply this number. So you're going to have 3 N's How many hydrogens? 12. phosphate anion, PO4, does that 4 apply to the phosphorus too? Think about that. Is there a bracket in front of the 4? No. Therefore, this 4 only applies to the oxygen. This P is by itself. There's only one phosphorus here. Phosphorus is 30.97. Now, how many oxygens do you have? 4. Now, if you add this all up and multiply as you are supposed to, you should get 149.06 grams per mole. If you don't get that number, you're probably doing something wrong with your calculator. Now, for most of you who have scientific calculators, your calculator will actually have parentheses keys or a parenthesis key on it. Usually it's right above like the 7, 8, or 9. If you do have the parentheses, you should use them. And use them in this fashion. So you're going to type in open parenthesis 4 times 15.99. Then you're going to have to close it. Plus 8 times 1.01. Now I'm just making numbers up. This is just for your edification. And then you can keep adding whatever you need to add in one step. Hit the enter button and you should get the correct answer. If you don't have the parenthesis key or it's not working on your calculator, you'll need to go through and multiply each of these terms independently, which means that you might have to write all this stuff down and do these things individually. Write all these numbers down and then add them up with your calculator at the end. I don't recommend doing it this way. There are a lot more places you can make a mistake in transferring numbers from your calculator to your paper, especially if you're tired or if it's late at night. Mistakes can happen, and then you're going to lose points for the whole problem if you're not showing your work and if you're just doing this on a piece of scrap paper. So if your calculator has the capability, I highly recommend practicing using the parenthesis key. If you have any questions about that, please give me a call. I will be happy to walk you through how to use your calculator. And with the internet the way it is, I can just Google your addition of your calculator, I can pull up a picture of it, and I can tell you exactly what buttons you should press. So don't worry about that. If you're having problems, just give me a call. Okay. Let's do a couple of examples. I want you to pause it and then come back and find out the answer. After I'm done writing these problems, I want you to pause it, and then I'm just going to write up the answer. I'm not going to work the problem out for you again. And I've noticed that from some of the questions you guys are asking me, I've been noticing that you haven't all been working out these problems and pausing the videos. So be sure that you go back and do that. All right, pause it. Practice? If you went back and practiced how to name these cripples. And there are your answers. If you get anything different than what I have here on the board, check your math. Okay, the mole. So back when chemistry was in its fledgling days, it was really a controversial issue talking about atoms, molecules, and that sort of thing, because some of it was talked about as heresy. You're talking about things that can't be seen or touched or felt. They're these tiny little particles. And a lot of people thought that it was going against God and the church to even talk about life at these tiny little bits of matter. So in order to make things a little bit more understandable, a man named Avogadro came up with some pretty important concepts or theories of thinking about these really small particles. So that's his picture. His name was Amedeo Avogadro, and he was born in Italy. A lot of great thinkers around the time of the Renaissance obviously came from Italy. And he was born to a wealthy family, which means that he had access to the best education, the best circumstances. He served his career as an attorney or practicing law as a solicitor. That wasn't really his passion. He was really interested in the natural sciences, so even though he was quite an accomplished attorney, he sort of switched fields and went into science. He developed the mole concept in 1811, and it was a really big deal. He's also known for his suggestion that equal volumes of all gases at the same temperature and pressure contain the same number of molecules. This is known as Avogadro's principle. We'll be talking about this a little bit later on. So this is the man behind the whole mole concept. So what exactly did he come up with? Well, he came up with this thing called Avogadro's number. This is the number, and for your purposes, 6.022 is all the digits you have to remember. You don't have to worry about anything past that. So when you're asked what Avogadro's number is, you will respond 6.022 times 10 to the 23. So what does this whole concept mean? Well, basically it means that there are this number of molecules or ions or atoms in every 1 mole of a substance. In other words, 1 mole equals that number, which is really big, number of particles. So what Avogadro was trying to do was trying to take a whole ton of numbers, lots of really small things, i.e., atoms, etc., and turn it into something that was visible, tactile, something that you could look at and study and observe. The mole. So the whole mole concept was revolutionary in chemistry. It gave chemists a chance to talk about something that was visible. For example, 1 mole of water molecules equals 18 milliliters. You know how much 18.0 milliliters is. In that small sample of water, 18 milliliters, that's not even a shot. A shot is an ounce, and I think an ounce is 30 milliliters. There are 6.022 times 10 to the 23 molecules. In that little tiny bit, only 18 milliliters of water. this is what the number looks like if you write it out. That's a really lot of molecules. That's why the whole mole concept became so important, because it was a way of quantifying a set number of molecules, but in a way that you could observe. So it was such a big deal that they have a special day for Mole Day. It's celebrated every year on October 23rd, hence 10 to the 23. And at 6:02 a.m. and p.m. it's a big, woo, it's Mole Day. Very exciting stuff here in the land of chemistry. Okay, so just to recap, the mole is a way to describe a quantity of atoms, ions, or molecules. This is important. 1 mole of marbles, now here we're talking about something that's quite a lot larger than a molecule or an atom, would cover the entire continental U.S. 70 miles high. Entire continental U.S. 70 miles high. That's a mole of molecules. Just a way of putting into perspective how big a quantity this actually is. But a mole of water molecules is only about 18 milliliters. And this little fellow is Augie. He is our little chemistry mascot. He's a mole, and he has safety glasses and a test tube. He's a good little chemist. Okay, so that's all the background that you really need to know about the mole. As far as background goes, let's take a look at Avogadro's number in chemical formulas. Okay, so if we take a look at water, H2O, we say that in this compound, in this molecule, there are 2 moles of H and 1 mole of oxygen. In 1 mole of compound. This is important because you can use this as a unit conversion factor. So if I had a question asking, how many atoms of H are present in 1.5 moles of H2O? You can use this as a unit conversion factor. So this is an example of why we spent so much time last week doing those nasty old unit conversions. So we're going to start in our first bracket with what we know. That's the 1.5 moles of H2O. And now the point of our exercise is to figure out how many atoms of H. So here our unit is moles of H2O. Now, if we were to right away calculate number of atoms, that would give us the number of atoms of, or molecules of H2O. So we need to convert here between moles of H2O and moles of H. This unit goes on the bottom. So in 1 mole of H2O, there are how many moles of H? 2. How do you figure that out? All you have to do is look at the compound's formula. Now, is this the unit we're looking for? Moles of H. We need number of atoms. So here is where you're going to use Avogadro's number. There are 6.022 times 10 to the 23 atoms every substance in 1 mole. So we can use that unit conversion factor in our last bracket. I didn't plan very well, so I'm going to run out of space. So in 1 mole of H, we have to cancel that out, so it has to go on the bottom. There are 6.022 times 10 to the 23 atoms. So if you do the math, you'll find that there are 1.8 times 10 to the 24 atoms of hydrogen in 1.5 moles of water. In our next video, we'll do more examples of this concept.